Human beings evolved for one place, Earth. Every bone, every muscle, every heartbeat was shaped beneath gravity. Our lungs expect pressure, our cells expect protection, our minds expect a horizon and solid ground beneath our feet. Take the human body away from Earth, and it begins to change. The spine stretches, the face swells, the legs become thinner, muscles weaken, bones lose strength, the eyes can deform, and beyond Earth's protection, radiation passes through the body, damaging cells as it goes. Then there is the question almost everyone has imagined. What happens without a spacesuit? You would not explode. You would not instantly freeze. But within roughly 15 seconds, you would lose consciousness. This is what space does to the human body. At first, weightlessness looks peaceful. Astronauts float effortlessly. Water forms perfect spheres. A gentle push can send someone drifting across a spacecraft. But they are not beyond gravity. They are continuously falling around Earth, along with the spacecraft itself. This creates microgravity, and the human body interprets it as a reason to begin dismantling itself. On Earth, muscles work constantly to keep us upright. The legs, back, neck, and abdomen all resist gravity. In orbit, that work disappears. There is no need to stand, no need to support body weight. The muscles receive a simple message: you are no longer needed. They begin shrinking. Strength falls. Endurance declines. After months in space, an astronaut may struggle to stand after returning home. Bones respond in a similar way. Walking and lifting place pressure on the skeleton. That pressure tells the body to keep bones dense and strong. In microgravity, weight-bearing bones are unloaded. Minerals begin leaving them. Calcium enters the bloodstream, then passes into the urine. This weakens the skeleton and increases the risk of kidney stones. To slow the damage, astronauts exercise for roughly 2 hours each day. They run while strapped to treadmills, cycle, and lift against resistance. The goal is not fitness, it is survival. Every movement tells the body, keep this muscle, keep this bone. You may need it again. But exercise cannot prevent every change. Within moments of reaching orbit, fluids begin moving. On Earth, gravity pulls blood towards the lower body. In space, that downward pull disappears. Fluid shifts towards the chest, neck, and head. The face becomes swollen. The eyelids grow puffy. The legs appear thinner. Astronauts call it puffy face and bird legs. The body believes it has too much fluid, so it removes water and salt, reducing blood volume. That helps in orbit, but when astronauts return to Earth, gravity pulls blood towards their legs again. Their reduced blood volume may not supply the brain quickly enough. They become dizzy, weak, sometimes they faint. The heart also adapts. It no longer pumps against gravity in the same way. Over long missions, it can become smaller and more rounded. This does not mean the heart is failing. It means the body is adjusting to an environment where the old workload no longer exists. The real difficulty comes later. Imagine traveling to Mars. After months in weightlessness, there is no recovery team waiting, no hospital. The crew may need to climb from the spacecraft, carry equipment, and begin working immediately. While their muscles are weak, their balance is disturbed, and their hearts are still adapting. The eyes may also change. Fluid shifting towards the head can affect the structures around the brain and eyes. The rear of the eyeball may flatten. The optic nerve can swell. Vision may become blurred. Some astronauts need stronger reading glasses in orbit. Scientists call this spaceflight-associated neuroocular syndrome. Some changes improve after returning home. Others may last longer. For a Mars mission, the question becomes far more serious. What happens after 1 year, 2 years, or 3? Microgravity also confuses the inner ear. On Earth, the brain uses gravity to understand direction. In space, there is no obvious up or down. Many astronauts experience nausea, disorientation, and headaches during their first days. Eventually, the brain adapts. Floating becomes normal. Then they return home, and gravity feels unfamiliar. Walking becomes difficult. The ground may seem to move. The brain must learn Earth again. Astronauts also grow taller, without gravity compressing the spine. The discs between the vertebrae expand. A person may gain several centimeters in height, but the stretching can cause pain, and the extra height disappears after returning to Earth. Yet weightlessness is not the greatest danger. Radiation is. Earth protects us with its atmosphere and magnetic field. Astronauts aboard the International Space Station remain partly inside that protection. But beyond low Earth orbit, the danger increases. Solar eruptions can send powerful particles towards a spacecraft. A severe event could deliver dangerous radiation. In a short period, astronauts may need to hide inside a protected area, surrounded by water, food, or fuel. Then there are galactic cosmic rays, high-energy particles traveling through the galaxy at nearly the speed of light. They can pass through spacecraft walls and through the human body. They strike cells, break chemical bonds, and damage DNA. The body repairs some damage, but not all. Over time, the risk of cancer increases. Radiation may also affect the eyes, heart, and possibly the brain. This remains one of the greatest obstacles to sending people to Mars. Then comes isolation. Astronauts live inside a confined machine, with the same people, the same walls, and very little privacy. On the space station, Earth remains close. Families can communicate, help can arrive, a return journey is possible. On the way to Mars, Earth would slowly shrink. Communication delays would grow. A question sent home might take many minutes to receive an answer. There would be no immediate rescue, no quick return. Every conflict, every illness, and every emergency would have to be handled by the crew. Isolation can disturb sleep, mood, attention, and judgment. And in space, a small mistake can become fatal. Then comes the final question: what happens without a suit? Imagine an astronaut suddenly exposed to vacuum. The first rule would be simple: do not hold your breath. The air inside the lungs would expand and could tear delicate tissue. The astronaut would need to exhale. Oxygen already in the blood would keep the brain conscious for only a few seconds. After roughly 10 to 15 seconds, vision would fade, consciousness would disappear, but the body would not explode. Human skin is strong enough to hold the tissues together. The body would swell as gases expanded. Moisture on the tongue, eyes, and inside the mouth would begin to boil, not because it became hot, but because the pressure was so low. Blood inside the veins would not instantly boil, because it remains under pressure. The body would not freeze immediately either. Vacuum contains almost no matter to carry heat away quickly. Lack of oxygen would kill far sooner. After unconsciousness, severe injury would follow. If the person were repressurized quickly, survival might still be possible, but the margin would be terrifyingly small. A spacesuit is therefore not clothing. It is a personal spacecraft. It provides oxygen, pressure, cooling, communication, and protection. Only a few layers of engineered material separate a living human body from an environment where it cannot survive. For missions near Earth, we have learned to manage many of these dangers. Exercise reduces muscle and bone loss. Medical teams monitor changes. Spacecraft provide pressure and oxygen. Earth's magnetic field offers partial protection. Mars is different. The journey may take many months. Radiation will accumulate. Muscles will weaken. Bones will lose density. The heart will adapt. Vision may change. Then the crew must land, stand, work, and survive. On another planet, Mars has gravity, but only 38% of Earth's. We still do not know whether that is enough to protect the human body during a long stay. The first Mars astronauts will not only be explorers, they will be experiments. Their bodies will answer questions that Earth cannot. Tonight, astronauts float beside the windows of the space station, watching continents pass beneath them. They see lightning inside storms, cities glowing at night, and the thin blue atmosphere protecting every human life from Earth. That atmosphere feels endless. From orbit, it looks impossibly fragile, a narrow line between life and vacuum. Space does not hate us. It has no cruelty. It simply exists, without air, without pressure, without warmth, and without concern for the life entering it. We are the ones trying to cross it, carrying bodies made for one small world into an environment that offers nothing they need.